Phuc is going to talk about his latest work with his friends on endpoint contribution to excited state modular Hamiltonian.
All right, so first I would like to thank the organizers for this great opportunity to present my work. So I will talk about some recent work with Dan Kabat, Gilad Lipschitz, and Deb Sarkar on endpoint contributions to the modular Hamiltonian of excited state. So this is the outline of my talk. So first I will give you some motivation for what we are doing. So basically I study the modular Hamiltonian of a class of excited states, perturbatively close to the vacuum, and there are some surprising effects. And then I will describe in the next section the perturbations due to inserting the stress tensor on the vacuum. And then in the next section, perturbations due to scalar insertions, and then due to higher spin operators insertions. And then I will conclude. So, again, what we are doing in this paper is study the modular Hamiltonian for excited states of the form some unitary acting on the vacuum. So the unitary U is e to the minus I epsilon g, where g is an integral over a Cauchy slice of some operator O with some smearing function f. And we will work to first order in the parameter epsilon. So in case you are not familiar with the modular Hamiltonian, here are some general definitions. So the modular Hamiltonian is related to the reduced density matrix for some subregion A by rho is the exponential of minus the modular Hamiltonian, and the reduced density matrix is obtained by tracing out the complementary subsystem from the full density matrix. Similarly, for the complementary region. So in quantum field theory, the subregion modular Hamiltonian H sub A, so A is the subregion, is a little bit of an ill-behaved operator. So it's better to talk about something called the extended modular Hamiltonian. So I denote that by H with a double arrow on top. So that's defined to be HA minus the modular Hamiltonian for the complementary subregion HA bar. And also we will talk about this operator delta, which I think is called the modular operator. So that's basically e to the minus the extended modular Hamiltonian, or in terms of the reduced density matrices, that's the rho of subregion A tensor product with the inverse of rho of A bar. So you have to be careful about whether this inverse really exists, but in the context of field theory, it should be safe due to the high amount of entanglement in field theory. So there is a naive expectation for what the modular Hamiltonian of these excited states should look like. And then I will tell you that the naive expectation will not be true, and there will be some surprises. But first, let me tell you about the naive expectation.
Hi, Phuc, can I ask a pedantic question?
Yeah.
Can you go back to your last slide?
Yeah.
So in equation 6, you're defining this as the tensor product of rho and rho A bar inverse. So just for the sake of argument, I can state I take a system in which both the subsystems are, unentangled. They're in their own pure states.
So a product state, in other words.
Yeah, and then rho bar A will have a zero eigenvalue because
rho bar A will.
Is that right? For a pure state, the density matrix has a zero. I'm worried that can you define the inverse? So
the inverse in general in a generic quantum mechanical system may not exist. The inverse of rho may not exist if rho does not have full rank. In quantum field theory, however, there's a high amount of entanglement in quantum field theory. It's the story of Tomita Takesaki theory, and so that there is a sense that in quantum field theory, thanks to this high amount of entanglement, the reduced density matrices actually have full rank, so it's invertible. But in
Okay.
general, I agree with you that row inverse is not, doesn't exist, may not exist.
Okay. Okay. Just a pedantic question. Thanks.
Yeah. So, okay, so the naive expectation, so this operator G, as you can see from my previous slide, is an integral over a Cauchy slice. So you can split it into the sum of an integral over the subregion A and an integral over the complementary subregion A bar. Can you see my cursor, by the way, if I highlight something on the screen?
Yeah, we can see your cursor.
Right. So, okay, so I can split G into a sum of those two integrals. And so the operator G would seem to be a sum of two operators, each of which act only in subregion A or in subregion A bar. And the unitary U, which is the exponential of G, would seem to factorize into a tensor product of two local unitaries, U sub A and U sub A bar. And all right, if I care about the reduced density matrix of subregion A, the U sub A bar has no effect, and the reduced density matrix for A is related to the vacuum 1 by the unitary transformation A. Similarly for rho A bar, the local unitary UA has no effect on rho A bar, and rho A bar is related to the vacuum rho A bar by this unitary transformation with UA bar. And because the modular Hamiltonian is nothing but the log of the reduced density matrix, the excited state modular Hamiltonian or extended modular Hamiltonian is also related to the vacuum 1 by a unitary transformation with U. To first order in epsilon, this is saying that the first order change in the extended modular Hamiltonian is basically the commutator of the perturbation G with the vacuum extended modular Hamiltonian. All right. So we would expect that this is the answer. But apparently there's more to it than that. Because we discover in this paper that actually there are unexpected contributions to the first order correction to the modular Hamiltonian associated to the endpoints or the boundary of the subregion. So we call that those contributions endpoint contributions. So those are in addition to the commutator term that I described in the previous slide. And the existence of these endpoint contributions can have to do with the fact that in field theory, the Hilbert space doesn't quite tensor factorize into spatial subregions. And so to give you the punchline, for a perturbation that acts on the null plane x minus equals 0, built out of an operator with spin n, or more precisely modular weights n. So this is the G, it's the integral of Jn with some smearing function f. The endpoint contribution will come out to be 0 when the spin is less than 2, and something non-zero when the spin is 2 or greater than 2. And the endpoint contribution takes the form of a light ray operator. So this is light ray operator is a topic of recent interest in CFT because of connections to the average null energy condition, etc. So I will now proceed to derive this answer in various cases. So first, let's consider the case of a stress tensor perturbation in a two-dimensional CFT. So Jn is T++, and we are in a 1+1 dimensional CFT. The perturbation G is the integral of T++ with some smearing F. And the endpoint contribution will come out to be something like this. So it's the light ray of the stress tensor multiplied by the value of F at the endpoint. Okay, so for the subregion, I will mostly consider the Rindler subregion in this talk. So this answer can be derived in two different ways. Way number one is by doing a conformal transformation on the vacuum modular Hamiltonian. And number two is by using the operator method. So number one is the faster way. And let me also, before presenting the derivation of the endpoint contribution, let me also mention that this endpoint contribution actually is, for some reason, exactly the same as some other endpoint contribution in the work by Faulkner, Ley, Parika, and Wang. In that paper, these authors did not consider excited state, but rather they consider the vacuum state, but the subregion is a small deformation of a half space. And in that paper, they saw that the modular Hamiltonian for such a deformed subregion also comes with this exact same endpoint contribution. So it's interesting that it's the same answer in a slightly different context.
Yes, sir, I understand. Just a question about the fz functions. Fz is a support function which peaks at z equal to 0, or is it something different?
You're asking about the support of the f of z function?
Yes, yes.
So far, I haven't assumed anything. It can be any function you like.
Okay. Okay. So long as it is a smooth function. I mean, you're assuming it's a smooth function.
Yeah, but I'm not sure if that assumption is essential. I don't. Yeah, I guess okay. It should be smooth. Fine. Yeah, yeah.
Can it be a distribution?
We did not think very hard along, about this type of questions. We just assumed that f is some sufficiently well-behaved function in some sense. Yeah.
Okay. Sorry, I missed something else as well. So what is special about z equal to 0? Sorry, I must have decoupled.
What is special about f equals f? Sorry.
Z equal to 0. Yeah. What is special about z equal to 0? Yeah.
Well, I guess so. If f has some non-zero value at 0, so if f has support at the endpoint of the subregion, so 0 or the origin is the endpoint of a half space. Right?
Okay.
If that is so, then I'm saying that there is such a contribution to the first order change in the modular Hamiltonian.
Okay, thank you.
And if f of 0 vanishes, then there is no such contribution, and all I'm left with is the commutator term. So this answer from my previous slide. Yeah.
Okay, thank you.
Sorry, can I ask a related question? It looks like f of z is holomorphic. Or is that
I'm kind of thinking about this integral as an integral over the t equals 0 slice. So it's an integral over a constant time slice. So z may as well be x, the spatial coordinate.
Okay.
Yeah. Yeah. So let me go through the derivation of the endpoint contribution by the fast way first. So by doing a conformal transformation on the vacuum modular Hamiltonian. So the vacuum modular Hamiltonian for a finite interval from U to V. So here I'm talking about finite interval first, and then I will take the Rindler limit later. So this is the answer. So there's some integral over z, and there's some integral over z bar, the right movers. So to go from here to the excited state modular Hamiltonian obtained by a conformal transformation, z going to g of z, we can kind of transform this operator. So this was done in work by these authors, that's Arutachan in India. And here's the answer. Where I have z, I replace by g of z. The measure these z changes in the standard way, and the stress tensor also transforms in the standard CFT way. And I ignore the Schwarzian derivative term because it's just a C number. And the modular Hamiltonian is only defined up to an additive constant anyway. So this is the excited state modular Hamiltonian. And now, but this is like the finite answer, because I'm only interested in the first order answer, the first order in epsilon. I set the function g of z to be z plus some small thing, so epsilon times some function f of z. So this is, in other words, a conformal transformation close to the identity. And then something interesting happens when I plug this choice of G of Z into this formula and expand to first order in epsilon. So when I do that, I get the following thing. So this is the first order change. So I have this expression. The first line of this expression basically corresponds to the naive expectation. So the commutator term, in other words, that I told you about earlier. You can check that explicitly using the commutator between the stress tensor and itself, and doing some integration by part. But the interesting thing is that we also have the second line. And you see the second line is only there when f has support at the endpoint. So f at v or f at u are non-zero. If they are 0, then you don't have the second line. So this is clearly a sign that the naive expectation that we thought is not valid, and there's more to the story. And also, so for the rest of the talk, I will mostly focus on the Rindler limit. So instead of a finite interval from u to v, I set u to 0 and v to infinity. So it's a half space. And then this big expression simplifies a little bit to this equation. All right. So, and I'm claiming that, okay, so the second line becomes this last term with f of 0. And so to gain more intuition for this term at f, with f of 0, we can do the following, kind of to gain a better understanding for why it has to do with the endpoint of the subregion. You can pick a profile f that is kind of very localized near the endpoint with a simple form of a rectangular function. So let's say it has support from minus b to a, where a and b are some small numbers. I plug this choice of f into this equation on the previous slide for delta h, sorry. And then I do some math. And if I send a to b to 0 at the end, I get, well, I get precisely that term with f of 0. So f sub 0 is the same as f of 0, by the way. So in this sense, it clearly has to do with the endpoint contribution. And it's a bit shocking because you would have thought that nothing is left, of delta h when a and b go to 0, because after all, the perturbation g goes to nothing, right? The support of g shrinks to nothing. So why would there be anything left of delta h? But, there is. So, okay. So hopefully now that I convinced you that there is this endpoint contribution, let's rederive the endpoint contribution a different way to make it even more convincing. So we will use the operator formalism. So again, let me focus on an operator g very localized near the endpoint. So integral of t from minus b to a for some small a and b. And how do we, so the idea of the operator derivation is the following. Okay, g is not going, so we want to decompose this g into a tensor product form, ga. So it's we want to decompose it as some operator ga acting on a alone with some ga bar acting on a bar alone. So the excited state then takes the form e to the minus I epsilon, this tensor product acting on the vacuum. And then I claim that for such an excited state, the delta h will come out to be given by this formula. So it's an integral over s. S here is basically the vacuum modular flow of some operators, okay? And it's actually a complexified modular flow. Okay, so the notation vertical bar sub s is explained here. So when I write an operator O with a vertical bar S, that means I take operator O and I flow it along the vacuum modular flow for time S. Coming back to this formula, you see it's a complexifying modular flow because it's S minus I pi here and S plus I pi here. And in addition, so I have something that I write as G with a tilde on top. So the G, so I'm skipping the derivation of this formula in the interest of time, but it's in our paper if you're interested in the details. So the G with the tilde is a certain notion of a mirror operator of the G A bar. And that notion of mirror operator, in the case where the subregion is a half space, is the same as the Cpt conjugation. So maybe I can say a few words about that. Basically, this notion of mirror operator is the same as conjugation by a certain anti-linear operator J in Tomita Takesaki theory, and that J for half space is the same as Cpt conjugation. And this formula is based on a formula previously derived by Sarosi and Ugajin for the delta H due to a generic delta rho first order perturbation of the reduced density matrix. So then we just spatialize the delta rho to the delta rho due to this kind of perturbation, and we derive this. So far so good. So all right, so now the hard part is to decompose this operator G, which is a smearing of T, into this tensor product form. To develop, so it may not be doable. So why do we even think that it's doable? So to see why it may be doable, consider the correlation function between G and T of Y, where Y is some other point. Using the usual two-point function of stress tensor in the CFT, we find the answer, this answer for the correlator between G and T of Y. So the notation here, sigma is basically the midpoint between A and B, and delta is the radius of the interval AB minus BA. Yeah. The important thing is that this correlator G with T of Y is singular when Y is A or Y is minus B. This suggests that indeed G can be decomposed into a tensor product of local operators at A with a local operator at minus B, or more precisely, a sum of such tensor product. So the nice thing is that we are working to first order in this perturbation. So you can consider, if we have a sum of perturbation, you can consider the effect of each of those terms separately and kind of add them up at the end. So, okay, so now that we see that it may work, what are the operators GA and GA bar? To identify those operators, we can consider the stress tensor three-point function, T of A, T of minus B, so at the two endpoints with T of Y. So this is the answer. And by kind of playing a little bit with this answer, we can come up with a series representation for the right-hand side of equation 29. So that's the G with T of Y correlator. So, okay, so there is this series representation. So this differential operator acting on this function of A, B, and Y is equal to basically this function. And this is a differential operator with infinitely many derivatives, by the way. The coefficients alpha sub n in this series can be determined quite explicitly. And they so the first few are like these. We haven't really studied questions of convergence, etc., of this series very carefully, but the coefficients seem to die down, you know, nicely. So it seems to be okay. And I should also say that the precise numerical values of these coefficients alpha n will not matter in the end. What matters is that we accept that there is such a series representation for the GTY correlator. So then you have this equality between GT correlator and TTT correlator. All right, and so now we want so now we know that at least inside a correlator with another stress tensor T, we can indeed decompose G in the form that we wanted. So you have this differential operator, and you can use the partial A minus partial B to the n. And you can use the binomial theorem to write it as a sum of product of partial derivatives. And so the whole thing will be an infinite sum of operators at A and operator at minus B inside a correlation function with T of Y. So we now want to lift that equality to an operator identity. So from this equality, it's tempting to simply strip both sides of the T of Y and say that, oh, we have an identity at the operator level. So you end up with something like this. So it may be okay, or it may not quite be okay, but in this case, it's okay. So to see that it's really okay, we can consider taking the correlation of both sides of this equality with some other operator X that is not the stress tensor. So you see, if provided that we don't run into some inconsistency, then we're probably fine. If X is the stress tensor, then we already know that we're fine. If it's not if it's not the stress tensor or in the conformal family of the identity, then actually both sides will vanish thanks to the conformal word identity. So for example, on the left-hand side, you would have the two-point function of T with some operator with a different spin, and that is 0. Right-hand side, you have three-point function of TT with some other operator with another spin. By the conformal word identity, that is basically a differential operator acting on the two-point function of T with a different spin operator. That also 0. So we are fine. So indeed it seems that we have an operator equality here. So then we can plug this representation for G into the formula that I showed you a few slides ago here for delta H in terms of some G. So if I do that, I have something, let's see, I have something like this. And now I kind of have to try to simplify everything as much as possible. So the first thing is to deal with the Cpt conjugation. So the tilde in this formula. Cpt conjugation basically flips the sign of the light cone coordinates x plus and x minus. So when on an operator like this, partial of t k time, you pick up a minus 1 to the k, 1 for each partial derivative. You also pick up minus 1 for each index, but there are 2 of them, so it doesn't do anything. So that's for the Cpt conjugation. And then let's see, we have to deal with the complexified modular flow also. So we can try to do that at the operator level, but it feels safer to do it at the level of correlation functions. Because actually there are pitfalls, dealing with the modular operator delta at the operator level. If you are curious about that kind of issue, for example, delta is an unbounded operator, so it's a well-known result in functional analysis that says that it cannot be defined everywhere on the Hilbert space. It can be at best densely defined. That kind of thing. So we didn't want to go into those pitfalls. So we kind of work at the level of correlation function. So in other words, we take the correlation function of both sides with some operator. And the only thing that can possibly yield an interesting answer is correlation function with another stress tensor T at Y. And also, previously we had s minus I pi, s plus I pi. Now we, instead of just, now we replace those by s minus IR for some r and s plus IR, and then we take the limit as r goes to pi. Because if you actually set r to pi already here, then you run into some ambiguity. So yeah, so we have this complexified modular flow, and because it's a half space, the vacuum modular flow is nothing but a Lorentz boost. So okay, so when you modular flow the stress tensor, the argument picks up e to the s, and you also pick up an overall e to the 2s because of the transformation of the indices. And we simply assume that this formula can be analytically continued for complex s. And also we will choose y to be negative. So this T of y is inserted in the complementary Rindler wedge, so that it's space-like separated from the other operators. And in that way, you don't run into issues with singularities, due to null separation, that kind of thing. So, okay, so then we just kind of evaluate this big expression. It's convenient to do a change of variable z equal e to the s, and then the whole thing kind of takes the following form. So there's a difference between two integrals over z, each of which has 3 points. The first integral has points at z equal -1 coming from here, z equal y over b coming from here, and e to the IR y over a coming from here. The second integral similarly has 3 points, 2 of which are the same as the first one, but the point at e to the plus IR y over a is now e to the minus IR y over a. So this factor is a bit different from this factor. In the limit as r goes to pi, those 2 points at e to the plus or minus IR y over a move, one of them moves counterclockwise, the other moves clockwise to hit the contour of integration. So as illustrated in this drawing, one of those 2 points hit the contour from above, and the other one hits the contour from below. This is why if you set r to pi at the outset, you just have some ambiguity because you have a contour on the, you have a pole on the contour of integration. Okay, so then in the limit when r goes to pi, you see these 2 terms on the previous slide become these two contour integrals with C1 and C2 running along the positive real Z axis and swerving around the pole from different directions, so above versus below. And then you can combine these 2 integrals into one closed contour, and because the integrand are exactly the same. And then when you do that, basically you just pick up the residue at minus y over a. And then the answer will take this form. So this is the correlator between delta H and T of y. And remarkably enough, this actually agrees with the answer that you would find if you take the delta H that I told you about, which is the light ray operator. So from a few slides back, I don't know where it is anymore. But yeah, so the point is that this answer is the same as the correlation between a light ray operator of T with T of y. So indeed, this identifies the endpoint contribution as the light ray operator of the stress tensor T. Moving on, I will now discuss the case of a scalar perturbation, unless you would like to ask some questions. Okay, so now scalar perturbation. I kind of do the same as before, but the perturbation is due to a scalar operator instead of the stress tensor. So the G operator now takes the following form. Integral of O from minus B to A. So you would think that it's natural to, so you see here I have set, so this second argument of O is the light cone coordinate x minus, which I have set to 0. You might think that why not just work with the perturbation on the t equals 0 slice as before, instead of the perturbation on the x minus equals 0 null surface as is written here. So the thing is that this is simpler because for the purpose of deriving, you know, that kind of tensor product identity, if perturbation on the t equals 0 slice, this O would be a function of both light ray directions, and that makes, and I actually could not, we could not derive an identity in that case. So we instead chose the perturbation to be situated on the x minus equals 0 null surface. And it's also a natural thing to do in view of the previous computation with the stress tensor in 2 dimensions, because the stress tensor in that case is a function of only x plus. So you have a choice whether to think about it as on the t equals 0 slice or on the null, on the Rindler horizon. You know, it's equivalent. So again, proceeding as before, we want to decompose this G into tensor product form. But is it doable? Well, so again, to kind of see whether it's doable in the first place, we consider the correlator of G with an O of Y. Using the standard 2-point function of scalar fields in CFT, we compute the G-O correlator to be such and such, so this equation. And again, as before, we see that the singular structure of this expression suggests that indeed G can be decomposed into a sum of products of operators at A and at minus B. Yeah. So we also, because these operators, this perturbation G is on a null surface, we will regularize it a little bit by introducing a small parameter theta, and kind of move the location of the endpoints A and B off the known surface a little bit and make them slightly space-like separated. One advantage of this regularization is that, you see, you can kind of drop these light cones from the displaced points to the t equals 0 slice, and think about these, the operator or the perturbation as an operator on the t equals 0 slice, and then it's clear that you have some operator, you know, with support in A bar, and some operator with support in A. So yeah. Also, there's a question of when we try to do this tensor decomposition of G, what are the possible operators sitting at minus B and A? So you may think that G, since G is built out of a scalar operator O, maybe the correct decomposition is into O and O. So O at A and O at minus B. But that doesn't quite work, actually. Because if you consider a correlation function with a different O, with a different scaling dimension, then you run into some inconsistency. Left-hand side, G with a different O would be a 2-point function, but it's diagonal in the scaling dimension, right? So it's 0. But the right-hand side, you have some O 3-point function, which is in general non-zero. So that doesn't work. And the thing that seems to work for us is to decompose G into O and the stress tensor T. So O at A and T at minus B. And because that kind of looks not very symmetrical, we symmetrized, and we add a second term, t at A and O at minus B. All right. So, yeah. So to establish the tensor product decomposition of G, we consider the correlator C of A, B, and Y. So yeah, so the square bracket is that symmetrized combination of O and T that I just mentioned, and we're taking the correlation function with another O of Y at Y. So by O at A, I mean not quite at A, you know, like on the Rindler horizon, but slightly regularized, like so. Similarly for T. And okay, this correlation function C can be evaluated using the TOO 3-point function in CFT, which takes us this form. So it's a bit complicated, but that's all right. Okay, because you know it's we have these non-separations. The correlation function will not be very nice. It will diverge. But if you just retain the leading behavior as theta goes to 0, and using the same notation as before, sigma A plus B is A plus B over 2, delta is A minus B over 2. In the end, you find an expansion of the following form. So the correlation function between G and O of Y is some differential operator acting on that symmetrized 3-point function C of A, B, and Y. And as before, the differential operator looks very similar to before, right? Infinite sum. The first few, it comes with some coefficients beta sub n, and they kind of look like so, the first few of them. And as before, we also want to lift this equation 56 to the operator level. So it's tempting to just kind of strip off both sides of the equation of the O of Y, and then you end up with something like this, the first line of this equation. But as you can see, there's a second line, plus corrections that I have written here. So the reason why there's a second line here is because just the first line doesn't quite work. So the reason why it doesn't quite work, actually it works in 2 dimensions. So if I am in 2 dimensions, I do not actually need any corrections here. But in higher dimension, I do need some extra stuff. And the reason why that is so is because, all right, so let me see. Yeah, so I was talking about coming up with an operator equation by stripping off both sides of this equation of the O of Y. And that naive step, which was very successful in the case of a stress tensor perturbation in 2D, actually is not so successful here, and some corrections are called for. And the reason why that is so is that so you can contract both sides with another. Let's see. You can contract both sides of this equation with another T, with another stress tensor, and on the left-hand side you have a 2-point function of O and T, which vanishes. The right-hand side, though, in general, TTO 3-point function is non-zero in higher dimension, so you have some trouble. But it's something that, but in 2 dimensions, you see, in 2 dimensions, it's nicer because you have on the local conformal symmetry. So the correlation functions are more strongly constrained. So actually the TTO 3-point function vanishes in 2 dimensions, and we will not have any such inconsistency. But in higher dimension, because of this kind of issue, you have to add corrections. So maybe let me discuss what are the possible forms of these corrections. We're not being completely explicit about what they are, but what they should be is like this. So one way to phrase this issue is that the left-hand side G is an operator over O. So it's some operator within the conformal family of O. Whereas on the right-hand side, you see you have the product of O and T, and you can use the OPE between O and T. And in general, in higher dimensions, you're gonna pick up all kinds of conformal families in that OPE. So what those corrections are designed to do is to remove the unwanted contributions from those spinning conformal families, all right? So then if you accept the existence of an identity of this form, then we can proceed as before. And again, we have to kind of compute what the mirror operators are. So they are just the Cpt conjugate. So you pick up these factors, -1 to the k, coming from each partial derivative with respect to x plus. And again, as before, we have to deal with the complexified modular flows of operators. So you have something like this. Once you plug this identity for G into that Sarosi-Ugajin-like formula for delta H in terms of the G. So you have something like this. And to make sense of the complexified modular flow, once again, we work at the level of correlation function instead of the operator level. And so we take the correlation function with another O of Y. Anything else will not give any interesting answer. So then you have this kind of expression for the correlation function delta H with O of Y. And again, as before, instead of dealing with S minus I pi or plus I pi directly, we replace that by S minus IR and S plus IR for some R that initially is 0, and then we kind of continue to R equal pi to avoid ambiguities. And we kind of chose the location Y of this O operator so that it's baseline separated from the other operator. So when Y, let me see. So when Y square is positive and Y minus is also positive, it's in the complementary, O of Y is in the complementary Rindler wedge, whereas everything else is in the original Rindler wedge. So you had T of minus B before you do the Cpt conjugation, but now it's T of B after Cpt, so now it's in the original Rindler wedge. So again, as before, we assume that the modular flow makes sense for complex values of the modular time S. And then you do some rearrangements, and then you introduce some notations like so: a tilde minus, a tilde plus, b tilde, theta tilde, etc. And then you end up with an equation of the following structure: the correlation function between delta H and O is some integral over S, so over the vacuum modular flow of something like correlation with G of A tilde minus B tilde. So inside the A tilde minus, there's an S dependence. And similarly for B tilde, with O of Y minus the same, but with plus instead of minus. So you see, this equation relates delta H to the perturbation G. So indeed, as you would expect, delta H is indeed an operator in the conformal family of the perturbation G, which is to say in the conformal family of O. And we did the same change of variable as before with Z equal e to the S, and then it becomes an integral like this over Z. Interestingly, the B dependence drops out between these two terms. So it can be said to be equal infinity, and then you have an equation like this. So it's as before. It's the difference between two integrals over z, and each of them has singularities. So the individual terms have points at z equals 0 and z equal -1. And also, when r goes to pi, there's actually a branch cut along the positive real axis that starts at z equal y squared over ay minus. In the first term, so in this term, that branch cut hits the contour of integration from above, whereas in the second term, it hits the contour of integration from below. So you end up with a contour that wraps around the branch cut as in this drawing. And it's convenient to deform the contour so that it wraps around the points at -1 and 0 instead of the branch cut. So you have to be a bit careful with the large Z behavior when you do that, but it seems to be okay. So you end up with some integral like this, where the contour now encircles the points at Z equals 0 and Z equal -1 clockwise. And to isolate the endpoint contribution, it's enough to set A to be 0. And then you have an integral like this. And then by doing this integral, finally, we conclude that actually there is no endpoint contribution in this case of scalar perturbation, unlike in the case of the stress tensor perturbation. So now the last part of my talk is to generalize the previous computations to arbitrary spins. So does anyone have questions, or should I keep going? Okay. So higher spin perturbation. Now we consider a perturbation G built out of spin Jn, which transforms with integer weight n under the modular flow. So like so, it picks up an e to the ns under the modular flow because it has n indices, and the arguments also pick up, the usual factors, e to the s, e to the minus s. So this is a generalization of the previous computations. The scalar perturbation case has modular weight n equals 0, while the stress tensor case has modular weights n equal 2. So now the G operator is like so. To proceed, you can either conjecture some identity to achieve the tensor product decomposition for this GAB, but we can also kind of skip that step and conjecture the following equality for the equation, for the correlation between delta H and Jn. Actually, we didn't exactly just skip the step of deriving the identity for tensor product decomposition, because actually in our paper, in 2 dimensions, we actually worked out that step carefully, but not so in arbitrary dimensions. But for the purpose of this talk, I will just simply skip to here, and maybe let's accept that there is an equality of this form, which you have already seen in the case of a scalar operator, scalar perturbation. So this is the same as that equation for scalar, except that you have a Jn instead of an O here, here, and here. And instead of, it used to be e to the minus s, now it's e to the s to the n minus 1. So that e to the s to the n minus 1 can be understood as arising from the way the G sub A comma B transforms under the vacuum modular flow. So it's an integral over J. So you pick up e to the ns because that's how J transforms, and the argument also picks up e to the s. And then you can do a change of variable and redefine e to the s x plus as the new x plus, and then you pick up you pick up this e to the n minus 1s times g of the boosted endpoints a e to the s, b e to the s. And then, okay, and then you analytically continue to s going to s plus or minus I pi, and then you have this minus sign. And then, so you have e to the minus e to the s to the n minus 1. And the same, I do the same change of variable as before, z equal e to the s. The whole thing becomes this integral over z, which has the same structure as what you saw in the scalar perturbation case. And by examining some spatial cases, so now the question is, what are the singularities of the integrand? By examining some spatial cases, we expect that this correlator G with Jn has a branch cut along the positive z-axis that starts at z equal y squared over a y minus. So this again sounds very familiar from the scalar case, right? And in addition, there are points at z equal 0 and z equal minus 1 that are only present for n smaller than 0. So z equal 0 comes from here, z equal minus 1 comes from here. Again, as in the scalar case, even though you have the b dependence here and here, they actually cancel between them. So you are left with no b dependence, and we may as well send b to infinity. And then you have with a ring around the branch cut. And because the large z behavior actually seems pretty nice, at least in a few spatial cases that we looked at, we can do the same deformation of the contour as in the scalar case and deform the contour to wrap around the points rather than the branch cut. And then you can strip off the Jn operator from both sides of the equality and then set a to 0 just to isolate the endpoint contribution. And then you have, for the endpoint contribution, you have this integral. And by doing this integral, we find the answer that I presented to you at the beginning of the talk, which is that the endpoint contribution vanishes for n smaller than 2, and it's something of the form of a light ray operator for n bigger than or equal to 2. So then you can ask why does this endpoint contribution only arise for n bigger than or equal to 2? And I can offer you some intuition for that. So the intuition that we offer in our paper is that endpoint contributions only arise when the perturbation G is capable of moving operators from A to the complementary region A bar, or vice versa along the X plus horizon. So to make this more concrete, we can take a scalar, we can just consider a scalar primary O inserted at the boundary between A and A bar. In other words, at X plus equals 0. And then look at the OPE between J and O. And we can ask when this OPE can generate. Well, so first of all, the OPE will generically have terms with derivative of O along some directions. But we care about whether derivative with respect to X plus of O appears, because that would mean that indeed this perturbation with Jn can move the O from A to A bar along the X plus direction, horizon, sorry. So the question is when can this partial derivative appear in this OPE? And to answer that, you can look at the modular weight of both sides of the equation. So Jn has modular weight n, so O has modular weight 0. On the right-hand side, well, we don't really know what Bn lambda is, but whatever it is, it's built out of the metric and the vector x mu. And just by looking at what the modular weights of the metric and the components of this x mu are, you can conclude that this Bn has modular weights either 0 or positive, but not negative. and because the partial derivative of O with respect to x plus has weight 1, coming from the x plus here, yeah, we see that this partial derivative can only appear in the OPE with an operator Jn with weight n bigger than or equal to 1. So that's already something. That's not quite exactly what we want to conclude, because we want to come up with n bigger than or equal to 2, right? That's the cases for which we found an endpoint contribution. So we have a more refined argument in our paper, not based on the OPE between Jn and O, but based on the equal time commutator between Jn with O. And that argument shows that indeed n bigger than or equal to 2 is precisely when you have an endpoint contribution. So this concludes my talk, but yeah, so let me summarize the findings. So we found that the extended modular Hamiltonian is sensitive to the details of the state, short distance details near the boundary between A and the complement A bar. So for states that are small perturbations of the vacuum, we managed to identify an endpoint contribution to delta H, which is surprising because you wouldn't have thought that it's there in the first place. Endpoint contributions take the form of light ray operators and only arise for n bigger than or equal to 2, where n is the modular weight of the perturbation. So a few future directions are we can generalize the computation to higher orders in perturbation theory. Maybe there will be some interesting structure that come out. We can ask, what about non-conformal field theories? So you see, the difficulty is that I have been using a lot of correlation functions in CFT, but non-conformal field theories, you don't know anything about correlation functions. So what can be done? So one venue for exploration is to kind of do everything using the path integral, because then you don't use correlation function explicitly, and then it may be easier to derive the same endpoint contributions for non-CFTs. And then even though the talk was entirely about CFT, so I haven't talked anything at all about ADS or the bulk. It will be interesting to see if these endpoint contributions imply something about bulk reconstruction, like what are they dual to in ADS? I don't know. Path integral derivation, so that's kind of the same. That kind of connects with the point I was making about non-CFTs. And then there's also some interesting connection to chaos, because this endpoint contribution, you know, under modular flow, it picks up some exponential factor, which kind of looks like the Lyapunov exponent in chaos. So actually, there's some recent work by authors, the authors Jean Debord and Lamproux, where they proposed some analogous chaos bound for the modular flow. So it will be interesting to see if there's some connection between our work and that line of investigation. So that's all I have to say. Thank you.
Thank you, Phuc, for a very wonderful talk. Are there questions from the audience? Yes, Karan Fernandez, please go ahead.
Yeah, I mean, I have two questions. The first one is, have you considered what happens to the relative entropy? What is the behavior of the relative entropy when you're considering these excitations? Like, do you still have the quantum focusing conjecture holding true? Like, does that set any conditions on F?
Yeah, so I have not thought very deeply about the connections to the quantum focusing conjecture or the ANEC or the QNEC. Yeah, it's an interesting question that I plan to explore more in the near future. But for now, I have not really thought about that.
Yeah, because it seems like that would be something which constrains the form of f. I mean, I got the point of taking a step function because you want like this distribution across the bifurcation point, but yeah, and I'm not entirely sure about your. I mean, the arguments that went into this n greater than or equal to 2.
Mm-hmm.
So I mean, that was a little fast for me. I mean, I actually got a call in the middle, so I think I missed that maybe perhaps, but how is the boundary contribution coming for n greater than or equal to 2? I mean, how is this physically justified exactly? Like, how are you physically justifying this contribution for?
Well, so the intuition is that we have an endpoint contribution whenever the perturbation kind of messes with the tensor factorization, right? So what is this endpoint contribution about? It's about the failure of, in field theory, of the Hilbert space to tensor factorize into the
right.
space.
I'm just asking, why is this true for n is equal to 2 onwards? Like, why wouldn't this also be true for a gauge theory, for example?
Gauge theory, well, so I mean, in this talk, I only I consider a CFT with or without an underlying gauge symmetry.
I see. Okay.
Yeah. So it will go through in the same way, even if you have gauge symmetry.
I see. So if you did have some gauge symmetry, then presumably you'd get this contribution as well.
I believe so. Yeah,
okay.
I believe so.
Okay.
Yeah.
Thank you.
Yeah.
Okay, so are there any more questions?
Phuc, you mentioned. Sorry.
Yeah.
Yeah, please go ahead.
Phuc, you mentioned at the beginning that the endpoint contributions that you found are the same as those that other authors had found for situations where the Rindler, instead of taking the Rindler subregion, you take some perturbation of the region.
Yeah.
Is that right? Do you have some intuition for why those are the same?
Yeah, I can offer some intuition for that as well. So in the work by Faulkner et al., the state remains in the vacuum. So it's not an excited state, but it's a slightly deformed half space. So the boundary between A and A bar is not exactly a plan, but it's somewhat curvy. So you deform it a little bit. And then they computed the first order correction to the modular Hamiltonian for the vacuum state for that deformed half space. So they actually did a path integral computation. So what they did was that they did they did a coordinate transformation such that in the new coordinates, the coordinate expression for the boundary between A and A bar is that of a plan. It's just a coordinate thing, but still it facilitates the computation. And okay, so then the path integral for the reduced density matrix of A picks up some first order correction under that coordinate transformation. So let's see, you're gonna have something that looks very much like a stress tensor insertion, because under coordinate transformation, the metric transforms in some way, and the variation of the action under changing the metric will be basically the stress tensor. So the computation looks very similar to the one that you would do if you actually excited the state with the stress tensor perturbation. And I assume that that's why kind of the same answer is found in the end. Yeah. I hope this answers the question.
Yeah. Yeah, I think that